Hello. In the previous lectures, we talked about different modes of data transfer, that is the programmed, interrupt, controlled, and DMA data transfer. In this lecture, we will be looking at different kinds of ports, input output peripheral ports. Okay. So when we are talking about ports, communication ports, this is in the physical aspect, right? When we say physical aspect, we are talking about which are the physical ports that we are using, how we are connecting devices. So ports can be, input output interfacing ports can be classified into two: serial and parallel. Okay, so serial means we'll be transmitting bit by bit, only one bit at a time. There will be one line to transfer data from one device to the other, and another line for the reverse transmission. So there will be some other pins also, lines also, but for data communication there will be one line from device A to B and another from device B to A. So that is it. In parallel interfacing, parallel data transmission, there will be say n number of lines. Like if it is an 8-bit transmission, then there will be 8 separate lines for each bit, and at a time you can send 8 bits of data, right? In serial communication, there may be one line for A to B and one line for B to A. There may not be. It depends on the specific condition. The takeaway should be that at any given point of time, from a device to another, you can send only one bit. So basically, in serial communication, if you want to send a word of data, then it is a series of communication. That's how the name serial communication comes from, right? And in parallel, if you have an n-bit word, there will be n lines, one for each bit of the word. Okay. In serial communication, again there are two types of communication known as synchronous and asynchronous. So let's see the different cases. So this is what I said about the communications. In parallel communication, for each bit there is a separate line from sender to receiver, and that is if this is an 8-bit communication. So the word size of this particular protocol will be 8 bits, and 1 bit is there for each. But in serial communication, there is only one line, and you have to send one bit after the other for each word. And at the sender side, there is a parallel to serial conversion, because within the processor all communication is parallel only. That is from memory to the processor, or the communication bus, any data bus, that is whether it is external bus or internal bus is always having a parallel communication. So when you are using some serial communication, you have to convert that parallel data to serial. For that you use parallel to serial conversion. Usually shift registers are used. Again, at the receiver side, the reverse has to be done. You have to convert the serial data to parallel data. Now coming to the specifics of serial communication. Again, like I mentioned before, there is asynchronous and synchronous communication. So this synchronous and asynchronous name comes from whether the clocks of the devices are in sync, right? That is the clocks, whether they are using the same clock, right? If it is a synchronous communication, it means that the clocks of both the devices are in sync, and this sort of reduces the complexity when it comes to the data that is being sent. there is this concept called as overhead for each block of data, but that is reduced. We'll come to that concept a little bit later. Remember this, for synchronous communication, the overhead required for sending data is reduced, and for asynchronous data, more overhead is required because there is no synchronization between the transmitter and receiver. The other thing is that asynchronous receivers are much cheaper to maintain. It's easier to implement, but synchronous receivers are not like that. It requires more hardware and it is more expensive, but it is much more efficient compared to asynchronous. Okay, this is how asynchronous and asynchronous data transmission can be visualized. In synchronous transmission, data streams are just sent. There will be a stop bit and a start bit. You can just send words or packets of data as such, because both the sender and receiver clocks are in sync. But for asynchronous transmission, each packet of data is sent in its own, right? There is no logical continuity. That is, if it is sent at time, a certain amount point of time, this can be sent at another point of time. It's not like they come in regular intervals or anything. So to identify these packets, where they start and where they end, some information is required. That is called as the overhead, given in the dark bits here, dark area here. But in synchronous communication, that is not required. It is anyway, the clocks of both the sender and the receiver are in sync, so the receiver knows that data stream coming from this time to this time is of a certain package, and the data coming from say T2 to T3 is of a certain data packet, like that. But in asynchronous communication, no such idea is there. So those informations, the packet number, where the packet ends, and if there are any corrections required, those kind of things, all those have to be given along with each packet. So in many cases, if you want to send 8 bits of data, you will end up sending 12 or 14 bits of data, because that much additional information is required. Okay, now let's see an example of a parallel port. So this one, SCSI, is called a small computer system interface. Okay, it is usually used to connect disk drives. Okay, may it be a hard disk or a CD drive or whatever. Usually it is used to connect disk drives to computers, but it may not be used in our PCs. Usually they are used in servers and things like that. Okay, let it be. The thing to note is that it is a parallel connection, and there are two types of SCSIs, narrow and wide. Narrow means it has a word length of 8 bits, and that means it will have 8 parallel lines for data transfer, and it can transfer 1 byte at a time. But the actual connector has 50 pins. Out of the 50 pins, only 8 are used for data transfer, right? 50 pins are there. So the other pins are used for establishing the communication, things like that. So much other data is being transferred. The wide SCSI actually has 16-bit word length, and it has a 68-pin connector. Right. So these are just different types of SCSIs, different generations, you can say. So anyway, there are just narrow and wide, but the data transfer rates change significantly, even within SCSIs having same bus width. Okay, the data transfer rate change depending on the technology and protocols being used. So this is a chart showing some of the pins of pin number 1 to 38 of a narrow SASI port. You don't have to remember this. I'm just showing this. See, if you look at it, only pins number 26 to 33 are being used for data transfer. Others are used for several other purposes, twisted pair ground, regular ground, reserved for some purpose. This is not used for anything. Then there is data parity check for the power, things like that. And again, these are the remaining pins. So if you look at it, so many bits are used for maintaining connections and other control purposes: ground, busy, acknowledge, reset, selection, command data, things like that. Okay, so whenever we are using some communication device, it's not just the data. There will be also other details, other requirements for establishing and maintaining a proper connection. So when it comes to parallel ports, some lines will be used for, obviously, for the data transfer, but remaining some will be used for other control and command purposes. Okay, the SASI uses a client server model in the sense that the client will be there. There will be an initiator and a target. Okay, so the initiator will be usually the device which starts the communication. In most cases, it will be the processor or the computer, and the target will be the disk drive that you are connected to the port, and it will be the initiator that it will act like a master. That is, it will be controlling and dominating all the data transfer. So it will set the protocol, the handshaking and things like that. So this is it with the SASI port that we use for parallel communication. But one thing to note is that the SASI in parallel form is now sort of outdated and not being used that much. And in general, parallel ports are being outdated, and most communication is that is peripheral communication is being shifted into serial devices, serial ports, or serial communication. Okay, the next parallel port that we will discuss is the PCI, or Peripheral Component Interconnect Bus. So earlier that SASI was connections used between the processor and a single device, right? But this PCI is PCI bridge and PCI bus is sort of like interconnection bus which connects our device, main device, which is our processor, to multiple devices, peripheral devices. That is how this PCI bridge and PCI bus structure comes. So this is the basic structure of PCI. So the PCI bus has basically three parts, let's say components, mainly the memory address space, the IO address space, and the configuration address space. So this IO, input output device address space, may be used, may not be used, depending on the designer. So the designer may choose to go for memory mapped IO instead of an isolated IO. It depends on the purpose or the designer. And then there is this configuration address space is used for configuring the plug and play capacity of the PCI bus. So these are some of the actual pins or control signals used in the PCI clock, and then the frame used by the device to indicate the duration of a transaction. Then there are the address lines. So these address lines can be 32-bit. This is an AD. AD means address bar data. So at a given point of time it will be data, sorry, it will be address, and at another given point of time it will be data. So there is a option to increase it up to 64. So it depends on the type of specific type of PCI connector or bus that you'll be using. Okay. Then there is command bar byte enable lines. Then there is a initiator ready and target ready signals. Then there is the device selector, and then there is the initialization device selector. So these are just some of the control or signals in general that is used for data transfer in PCI bus. So this is a timing diagram. This sort of diagram is called as a timing diagram of a basic read operation on a PCI bus. Okay, so these on this side you will see the different let's say signals that we saw, and this is how they vary on the changing clock cycle. So this clock cycle, this clock signal is the base signal that will be using, and for each clock cycle there will be changing, right? So this frame signal will be initially it will go down, it will be 0 for certain amount of time, and in this AD line, so initially the address will come, and after some time, approximately one clock cycle, the different data will come. And in this control bar byte enable, command bar byte enable, for initially the command bits will come, after that the byte enable bits will come. Similarly for each lines there will be a change. Don't have to memorize this, I just wanted to show how these signals are changing. So that's it regarding the PCI bus. Next we will be moving on to the USB. But before going into USB, one more thing to take note in PCI is that PCI being a parallel port, now that too is being converted into a serial port communication, which is called as a PCI Express. So now let's move on to the USB. Okay, USB, which is Universal Serial Bus. So the main purpose of USB is to bring a uniformity regarding the ports, because before USB was introduced and standardized in devices, each device had a separate type of port and it was difficult to manage. So USB came into popularity mainly due to its flexibility, right? And the other thing is that if you have one parallel other specific port other than a USB port, once that is used, it was not able to expand other regular parallel ports like a PCI or things like that. But the thing with USB is that because of its structure, because how it is designed, it is easier to expand it to a certain point. So that is the two main advantages, being the universality, standardization, and the expandability. Then there is the convenience factor of plug and play. So flexibility and low cost being one of the main advantages of USB. The other thing is that it is following an asynchronous mode of transmission. So the device which is being connected to the processor, the computer need not be in sync with the clock frequency of the processor. Okay. Now to accommodate the requirement that the USB should be expandable, it follows a tree structure, right? Tree structure is something like this. There will be one root hub and there will be intermediate hubs, right? So each device you connect, each USB device you connect to the root hub, it can be a hub or an IO device depending on how you go and connect. So once you have a connection here, and if you connect another USB device to this, if it gives the facility, then this device will become a hub, and the devices connected to this hub will become the IO devices. This is very easily understandable that you can buy USB hubs for expansions, right? You buy a USB hub and you plug into one USB port and you have 3 or 4 different USB ports. It is using this tree structure that expansion is possible. So we talked about the structure. The other thing is that how data is being transferred from the root to the different input output devices, that is from the host computer to the IO devices. So it is basically when the data is transferred from the host computer to the nodes, the input output devices, the host basically broadcasts, that is all information, any information coming from this host computer, it goes to all the devices, right? Anything coming from here, it goes to all the devices, and only the required device will take the data. But when it comes to the other way, that is when a specific device communicates, it won't broadcast, it will just communicate upstream, that is it will communicate through the host only. So by this method, the host computer can communicate with all devices, and all devices can communicate with the host, but devices can't communicate with each other, right? So this IO device cannot communicate with this IO device, it can only communicate with the host computer. That is a consequence or effect of the USB tree structure. So again, this being an serial communication and asynchronous communication, data is sent in the form of packets, and there will be, each packet will have data parts, and the data will be having some sort of overheads. The other thing is that there will be control packets, right? Control packets are used for the initial establishing of communication link with the IO device, acknowledging that data has been transferred, initializing data transfers, things like that. So 2 types of packets are there, communication are there, control packets and data packets. So that is it with our USB communication, and I am winding up the session on ports, interfacing ports with this lecture. In the next lecture, we will start with the memory systems. Thank you.